Hi guys, welcome to this next video on the integration of Trig products. Now what this is referring to, probably best once again if I refer to a specific example here. Okay, so here is a question I'm going to take from your workbook. It's page 188, question number 109, and as you might be able to see here, if you look carefully, you've got the sine function multiplied by a cosine function. Yes, it's sine 5x and cos x, and there's an 8 as well, but essentially we've got two trig functions being multiplied together here. Now one of the problems that we're going to run into here is that there is no equivalent of the product rule for integration. Okay, so what we're going to need to do is to make use of a group of what are called trig identities. So this group of identities here, now what an identity means is that if A and B are different angles, then this left hand side is equal to the right hand side for any particular angle A and B. Now these identities can be proven, but for now we're going to assume that they are true. And this is one of the things I loathe to do, is to make assumptions and simply tell you that things are true. So what I will do is to post some links to the proofs of these identities here. Okay, and you can have a look at that if you're interested. Okay, so for now we're simply going to assume that they are true. Now there's going to be some other identities that we're also going to use. This is one that you've seen before, cos squared of an angle plus sine squared of an angle equals 1. Now if you divide that, what I'm going to call equation 1, through by cos squared x all throughout there, you end up with 1 plus tan squared x. Sine over cosine is tan, so sine squared over cos squared would equal tan squared, and 1 over cosine is secant, so 1 over cos squared would be sec squared x. So this is another identity here, this one we're going to use at times. And if you divide equation 1 through by sine squared, for very similar to reasons to what I just mentioned for the one above, you end up with cot squared x, 1 over sine, sorry, let me just come back to that one just for a moment. Yeah, that was correct, I was just looking at the wrong equation here. Cosine over sine is going to be equal to the inverse of tan, which is cotan. So essentially, if I just put that over here, a little bit of explanation for that one, you end up with cosine squared over sine squared plus sine squared over itself equals 1 over sine squared, and this can be written as cos over sine all squared plus 1, and 1 over sine is equal to cosec, so this is cosec x all squared, or cosec squared x in other words. Cosine over sine, well that's the same as the inverse of tangent. Now how's that coming about? You might recall that sine over cosine is equal to tangent, therefore the inverse of that would be cos over sine, which is 1 over tan. So this can be replaced with 1 over tan all squared plus 1 equal to cosec squared x, and 1 over tan is known as cotan. So we end up with that identity right here. Okay, so let's get rid of all of that, make some room again. spend a bit of time erasing all of this. Okay, so that's another couple of identities, and finally there is this group of identities here where cosine of 2 times an angle is equal to 2 cos squared x minus 1. Once again, I will prove that. We'll put a link to a proof of that later. Now if you make cos squared x the subject, you end up with that identity there, and it's another identity for cos 2x in terms of sine. It's 1 minus 2 sine squared x, and if you make sine squared x the subject of that, you end up with this identity here. Now, why are we going to be using those identities? Well, the reason is we can't integrate a product, but if we can write the product as a sum, then we can integrate each part separately. So I think that's best shown with an example here. So let's take this one here. Now this is sine times cosine, so probably this first identity would be the one I want to use. Now this has got a 2 in front, this has got an 8 here, but if I simply take 4 as a factor out the front and leave the 2 there, then you can see that we can apply this identity directly. So it would equal 4 times, okay, now we're going to take this 2 sine 5x cos x, use this identity to write it as the sum of 2 sine functions. So it'll be the sine a plus b. Now a is 5x, b is x, so you get 6x plus the sine, according to the identity it's sine, a minus b, so it'd be 5x minus x, which is 4x, and it's going to be all of that integrated. And since it's now a sum of 2 sine functions, we can simply integrate each sine function in turn. But of course we've got a 4 out the front, so let's do our integration and let's make sure that we have that 4 out the front. So I tend to put the 4 there, then a big square bracket. Now integrating a sine function is going to give negative cosine, and because all the work that we did on integrating sine functions, I hope you can see that this will give negative 1/6 cos 6x, and this one here will be negative 1/4 cos 4x, okay, for the two integrals of each of these here, plus c. And let's multiply the 4 into that now. So we're going to get negative 4 times negative 1/6, 4 times negative 1/6, negative 4/6, same as negative 2/3. Cos 6x, and 4 times negative 1/4 will simply become negative 1, so minus cos 4x, and our constant at the back. Okay, so there's our first example, and if you check the back of the book, that's the answer they have as well. Okay, let's take a look at a second example, and I'm going to take number 117 from your workbook, okay, where it's got 4 cos squared x. Now cos squared x and a 4, what can we do with that? Well, here we go, this is this cos squared x one. I can rewrite that like that, so let's do that, and let's take that 4 out the front. So according to our identity, it should be a half, and let me just tidy that up. Yes, I do need the bracket. Cos 2x plus 1. Right, let's tidy this up. 4 times a half is 2. I'm going to put that 2 at the front. And then it's going to be the integral of cos 2x plus 1 now. let's move the working up to here. Okay, so this will be 2 times, and now let's start integrating. So big square bracket, cos, integral of cosine is sine, and once again because of the chain rule, be a half sine 2x. Check that by deriving it, and you should get back to cos 2x. Integral of 1 won't be 0, that's differentiation, it's integration, so it becomes x plus c. And 2 times a half is 1, so sine 2x. 2 times x is 2, so plus 2x, and our constant. Okay, and once again, check the back of the book, that is the correct answer. Okay, and we'll do one last example here. Okay, so let's make a new page, and call this example 3. And let's take something which is not straight from your book. Similar though to the previous example, but just to show you one that involves tangent. So what we can do with tangent, okay, let's have a look at these identities here. Here's one involving tangent. Okay, 1 plus tan squared x equals sec squared, and if you check that table of integrals on page 174, yes, there is an integral of sec squared, which is tan. The derivative of tan is sec squared, so the integral of sec squared is tan. So I can integrate sec squared, and I'm going to replace the tan squared x then with sec squared x minus 1, moving that 1 over here. So let's go back to that page, and we're going to rewrite this then. I'll pull the 3 out the front. Okay, and this is going to become sec squared x minus 1. And I think we're now in a position to just straight integrate. So 3 times the result. Integral of sec squared is tan. Integral of negative 1 would be minus x, and our constant. So final answer, 3 tan x minus 3x plus c. Okay, so there's 3 examples. I will put a couple of questions up that I'd like you to do, and you can actually check the answers for these, because I'm going to put up a couple of questions that come from your workbook. Now, one thing I'd ask you to do is not to check the answers at the back before you do them. Okay, so just have a go at these 2 questions and see how you get on choosing one of the answers from the multiple choice here. Okay, so good luck with that, and I'll see you in class tomorrow.